In this video, I'll show you how to draw Lewis structures of molecules loaded into the program Moilin. If we start with a very simple example, carbon monoxide. Carbon monoxide contains one carbon atom and one oxygen atom. To get its Lewis structure, once it's loaded into the program, you just press this button here. In the Lewis drawing, bonded electrons are shown in black and non-bonded or lone pair electrons are shown in blue. In carbon monoxide we can see there are 6 electrons in the bond. It's a triple bond between the carbon and the oxygen, and the structure has a negative charge on the carbon and a positive charge on the oxygen. These are often referred to as formal charges. Now if we look at another example, if we look at azide ion, azide is N3-, there's a single negative charge on it, and if we get the Lewis structure of this case, we see that in the structure the nitrogen atoms have double bonds between them, the terminal nitrogens have -1 charges, and the central nitrogen has a +1 charge. This is an overall charge of -1. So it's very easy to get the Lewis structure on molecules like this. Now if we look at another example, if we look at nitrobenzene, nitrobenzene has a benzene ring with a nitro group attached to it. The nitrogen in the nitro group is here, it's blue, and the 2 oxygens are red. Now if we ask for the Lewis structure of this case, we can make the electrons slightly larger to make them more visible. We can see we have the familiar benzene ring here with 3 double bonds shown, and the nitro group here. Now you can also rotate the structures with mouse down movement. We can see that the nitro group, the NO bond on this side is a double bond, and the NO bond on this side is a single bond with charges across the bond, +1 on the nitrogen, -1 on the oxygen. Now if we go back to the carbon monoxide example, we can see another feature of the program. It's a useful feature that's sometimes called bow and arrow chemistry. In bow and arrow chemistry we can move electron pairs and structures. This is often useful for examining reaction mechanisms, but in the present case we want to look at bonding using this. We can move electron pairs here by starting the function by clicking there. Now we have 6 electrons here between the carbon and the oxygen, indicating this is a triple bond. Now we can actually move one of these pairs from the bond to the oxygen atom, and when we do that we see that the charges on the atoms disappear, but the bond is now just a double bond. So if we put the electrons back by moving a pair of electrons from the oxygen into the bond, we see that the charges come back. The reason why there are charges there is because when you form a donor bond, that is a bond which is formed by taking a pair of electrons from one atom only and putting them into the bond, then carbon has a -1 charge and oxygen has a +1 charge, to recognize the fact that in donating a pair of electrons into the bond, the oxygen has lost 1 electron and the carbon has gained 1 electron. This is a simple electron accounting. Now we can look at another example of this. If we go back to the nitrobenzene case. Now the nitrobenzene case has the familiar Kekulé structure of benzene, and of course you can use the bow and arrow chemistry to move the electrons around the ring as you would expect. In other words, to shift the double bonds from these 3 bonds to the 3 bonds that are single bonds. By just clicking the electrons you can move around the pair of electrons until you have moved the double bonds to the other position. Now it's also possible to move the bonds down here so that the charged bond, which is on this side, moves over to the other side. You can do this by moving a pair of electrons from the oxygen there into the bond. The nitrogen exceeds the octet. We must then move the electrons from the bond out to the oxygen, and now we see the charged bonds on the right and the double bond is on the left. Another example which shows the usefulness of the bow and arrow chemistry is the structure of N2O. N2O consists of a NNO system, and the structure, it's an overall neutral molecule because the +1 -1 charges cancel, of course, and the structure that's drawn by the program shows us that there's a nitrogen double bond and nitrogen oxygen double bond. Now this is just one resonance structure for the molecule. It's believed that another structure is more important because it's known that the nitrogen-nitrogen distance is shorter than the nitrogen-oxygen distance. It's believed that this bond has more triple bond character. Now to achieve that, we just need to move electron pairs. We can move an electron pair from the nitrogen into the bond, and we would predict now that this would cancel the charges on these two, because if we move an electron pair from the nitrogen here into the bond, this nitrogen will become +1, which the -1 will cancel with, and this nitrogen will become -1, again +1 will cancel. So the charges have gone as expected, but the nitrogen now exceeds the octet because it has 2, 4, 6, 8, 10 electrons, which is not possible. It's exceeding the octet. To restore the octet, we just need to move a pair from this bond onto the oxygen. And this is what some people consider to be the more correct resonance structure, or the more important resonance structure for N2O. In this way, you can get Lewis structures of any molecule loaded into Moilin, and you can then move electron pairs around in the structures.